The Vadose Zone is important to us because it's right under our feet. That's the subsurface region that we're going to interact with most closely. Here's one example. This is the Thistle landslide in Utah. You can see the slide is right here, and it broke loose from the hill slope, went down, and crossed this valley, and created this lake behind it. And there's a great deal of concern about the potential for that lake breaching this natural dam. And the Oso landslide has been in the news a lot lately. That was a landslide up in Washington State that came down, and very tragically, there was significant loss of life as a result of that. So we're interested in how landslide processes work, and water in the Vadose Zone plays an important role there. And of course, we're interested in how our food is grown and that agricultural practices are successful, and that involves water in the Vadose Zone. Contaminants are often released in the Vadose Zone, and in some cases, they migrate through the Vadose Zone and get into the saturated zone. And we need to store nuclear waste somewhere at some point. This is Yucca Mountain, and for a long time we thought we would put our nuclear waste there. The water table is very deep at this location, and so the waste would be disposed of, stored in the Vadose Zone. So what do we mean by the Vadose Zone? Well, I would call this the region between the ground surface and either the water table or the capillary fringe. So this is the water table, and that's defined as the surface where the pressure head is equal to 0. And then right above the water table, there is a zone where the pores are saturated, but the water pressure is less than 0. That's the capillary fringe. And the lower boundary of the Vadose Zone is somewhere between the water table and the capillary fringe, depending upon who you talk to. I think for our purposes, it doesn't really matter. It starts at the ground surface and it goes down to somewhere in here, and the specific lower boundary doesn't really matter. For the most part, the pores in the Vadose Zone are filled with water and air. They have both phases, so they're unsaturated or partially saturated. Although there could be zones where the water is locally saturating the pores. These would be a perched water table, perhaps. And so what we're going to be interested in is how to characterize the storage of water and the transmission of water through the Vadose Zone. There are many applications for this, for the storage and transmission of water through the Vadose Zone, from agronomy to soil physics, the classification of how soils are created and developed, some civil engineering applications, and of course in hydrogeology. So the agricultural applications are going to be very important because this is where much of our food comes from. Flow and storage of water in the Vadose Zone affects crops. In general, the water has to flow through the subsurface in the Vadose Zone to get to the roots, but air has to flow as well to aerate the soil and bring in oxygen. So the structure of the soil, the hydraulic connectivity is important, and how the chemicals move through the subsurface in this in relatively shallow Vadose Zone is also important. In general, you want to have some drainage. The pores need to be able to drain by gravity for agricultural purposes, but not too much. So the soils have to retain some water, but not be saturated. Also, issues related to the strength of soil, how sticky they are, will be important for plowing and planting. So soil physics is the process or the discipline that is focused on the movement of water and solutes through the shallow Vadose Zone. it really came out of the agronomy field and the need to better understand how water moves through soils to grow crops. Some soil physics is also involved with mechanical aspects related to erosion and plowing. And soil chemistry, that's a subdiscipline that looks at chemical reactions and transport of compounds, nutrients, for example, and it has a variety of applications, but it was primarily motivated because of applications in agronomy. And then also soil development and classification. The initial interest in understanding soils and being able to classify them and describe them was really motivated by these agricultural applications. And so all of these subdisciplines really feed into the agronomy application, and they're all important for land management. How do you decide what to do at a particular field in order to maintain the ability for it to produce crops? And you can see, for example, over here, there were some poor management practices that led to this high erosion, and you can imagine that it would be difficult to get a tractor through this field and plow it. So civil engineering is another field that is heavily reliant on Vadose Zone processes. We like to build a lot of things, and we generally are going to build them on the Vadose Zone. So understanding the strength of soils has an important implications for the bearing capacity of foundations, and it also is important in understanding slope stability and landslides. And I have an example here of a coastal landslide where this slope has been unstable and slid away, and you can see that it's encroaching on these houses. And more subtle soil problems. Here's some cracks in vertisol. That's a type of soil that undergoes a lot of shrinking and swelling when the moisture content changes, and this kind of thing can cause issues with cause problems here with cracking of foundations. There's an example. So other aspects of the Vadose Zone that are important in civil engineering: permeability for draining out foundations, flow through landfill liners and caps. Typically, civil engineers will be the people that design landfills. And here's an example. This is a cap on a landfill in Fairfax County, and this cap is put over the landfill to really limit the amount of water that's flowing into the landfill. The idea is that if you can limit the amount of water that flows in, that's going to limit the amount of water that is flowing through the landfill and leaching out the waste. So infiltration is also important because infiltration will be what determines how much water there is that is available for creating a flood in a rainstorm. If you have rain and all the water infiltrates into the subsurface, then the rate at which it goes to the stream will be slowed down, and so that will tend to reduce the amount of flooding. But if the water that falls as rain very rapidly runs off, then that causes the water to accumulate quickly in a stream and increases flooding risk. Erosion and sedimentation, that's going to be important for a variety of civil engineering, construction type of applications. Filtration of solids in septic systems, and then a variety of other things here. Soils move around, they shrink and swell, they shrink and swell when the moisture content changes, and we saw this example over here. They also will change volume when they freeze. So frost heave is an important aspect where you have soils that freeze often, so up in the northern climates. And then there are also a variety of chemical effects that are important in civil engineering. And in hydrogeology, we have some of these same processes, but also some things that are really distinctly in the realm of hydrogeology. So, under geology, the geo part of HydroGeo, weathering of rocks is taking place in the Vadose Zone, along with the development of soil and the erosion and development of a landscape. So, really, the field of geomorphology, at least to the extent of the formation of landforms in upland areas, is concerned with processes that are occurring in the Vadose Zone. Here's a nice example of some landforms that developed as a result of the erosion of soils, very deep erosion that accompanied some poor farming practice back in the 1930s. This example is up in Ontario. It's called the Cheltenham Badlands. And you can see that it's just the soil is just completely removed and nothing is growing there. As it turns out, the region around Clemson, the region, the Fans Grove region, where we'll be working for the last part of field camp, and really the region just even fairly close to campus, looked like this back in the early part of the 1900s as a result of poor practices that were done with cotton farming. The agricultural practices were switched over to growing pine trees, which could grow on very poor, degraded soils. And so you'll see a lot of the Fans Grove area is now in pines. And we don't have these bare landscapes like they have up in this area in Ontario. But nevertheless, the processes of erosion and soil development are of interest to hydrogeology and geomorphology. And so, in the hydro aspects, well, if we're just going to focus on aquifers, for example, then the process of recharging the aquifers will really be fundamental to how aquifers work, and the recharge process occurs through the Vadose Zone. So we have water falling as rain, for example, reach on the ground surface, and then how that water goes from the ground surface down to the aquifer is the recharge process, and that is something that occurs through the Vadose Zone. We're also interested in flow in the Vadose Zone itself, the partitioning between flow that goes in the downslope direction and flow that maybe is percolating downward for recharge or perhaps evaporating. And to this end, the flow in the Vadose Zone through fast paths or macropores. These would be root holes or wormholes or cracks. A small portion of the pores that are unusually large allow the water to move unusually quickly. And so this will be important for understanding how storm flow develops. And then also evaporation and transpiration, how trees or other plants will pull water out of the subsurface through their roots and transpire it out into the atmosphere. That'll be really, in most places, that's the major component of the water balance is ET. More precipitation is removed as ET than any other component in the water balance. And then also because contaminants are typically released in the Vadose Zone, if we're interested in the environmental aspects of hydrogeology, then understanding how contaminants move through the Vadose Zone, how they might be recovered or degraded within the Vadose Zone will also be an important aspect. And all of this comes back to really needing to understand how water is stored, the origin and the meaning of pressure in the Vadose Zone, how it flows through the Vadose Zone. Those are all fundamental processes to these applications. Okay, so what I want to do is cover these main topics: how soils form, how to describe them, how water is stored, how it's transported through the Vadose Zone, and how reactions are occurring. So, soil formation. Well, we start off with superficial geological deposits. And there are a variety of ways that deposits can be formed at the surface. Wind-blown deposits are aeolian. That's one approach, one possibility. Waterborne or water-transported contaminants or alluvial deposits. Glaciers can move the superficial deposits around and leave behind a very characteristic deposit. Glacial drift is kind of a catch-all name for a variety of different types of glacial deposits. We can have superficial material moving downslope. This is called colluvium. And material that is weathered in place and may in fact retain a relic structure, or sometimes the processes in the Vadose Zone are sufficient to just destroy the relic structure. So saprolite is an example of residuum where the relic structure of the parent rock is intact. And then there may just be rock materials. So if we start with these deposits, then pedogenesis is the formation of soil horizons or solemn that are created on these deposits. So this is a superficial geologic process formed by one of these things. And then there are processes related to rainfall, bacterial growth, the growth of plants that cause various reactions, chemical reactions, and mechanical processes that form layers within the superficial part of this material. And this is what we call soil, or these soil horizons or solemn. And here's an example of these different layers. So there's several different layers or soil horizons formed in this material shown in that example. So there are going to be three main processes that we'll be interested in when we're concerned with the formation of soils. Biological processes. These are plants, microbes, animals that will modify the composition and the structure of the geologic deposits. Plant roots will produce extracts or produce compounds that will break down soil materials, that will break down rock minerals or break down minerals, the components of rocks, and extract nutrients. And roots are also really good at physically disrupting soils. The roots can penetrate down into the soils, and also here's an example where a tree has spread its roots and then toppled over and disrupts the soil by, well, pretty clearly quite a lot. This is a very large tree, but if you walk through the forest, you'll see that this happens on a smaller scale, but still a very significant scale in any kind of forest. So microbes are going to be particularly important because they're going to be creating chemical compounds that can break down minerals. Their nutrients or their waste products may also be important in degrading minerals, and the microbes themselves are going to be associated with the rhizosphere. With basically it's the microbes that form on the roots that are conducting a lot of the chemical reactions that will be interacting with the soils and doing the biochemical reactions. And then there are a lot of critters that live down in the Vadose Zone at shallow depths, animals and insects. The subsurface provides a nice refuge place for them to go and hide from predators, and so they burrow down and they're looking for nutrients or safety. And here's an example. Here's an earthworm that is burrowing down, and so this earthworm is doing its thing, and so it's changing the subsurface chemically, but it also creates a burrow that will affect the water flow in the subsurface. And you can also see some cracks here that will affect the subsurface flow. So there are chemical processes that will also be important, and many of the chemical processes are tied closely to biological processes or biochemical processes, but there are also just standalone abiotic chemical reactions that are important. The weathering of parent minerals, the altering of them, production of clays, dissolution of the component minerals into soluble phases that are then washed away. That's going to be really a fundamental process that occurs in the Vadose Zone to form soils. EH and pH conditions, the redox and the pH conditions will be an important process that affects the speciation of minerals. So with a certain set of constituents, the EH pH conditions will determine what what chemical species occur there. Sometimes these conditions favor dissolution, and sometimes they favor precipitation. One thing that happens in soils that can be pretty striking is the precipitation of calcium carbonate to form caliche. This forms a very hard layer that can be difficult to dig through or hand auger through or penetrate. Carbonic acid from CO2 and respiration of plants, microbes. This forms low pH and is responsible for degrading compounds, degrading minerals, and dissolving carbonates, for example, and other reactions that are important in the Vadose Zone. Physical processes involving flow will be important. Flow of water, particularly water infiltrating from the surface going down. Gases exchange through the Vadose Zone. They exchange with the atmosphere. That's going to be important. Mass transport of nutrients dissolved in the water or colloids that are in the water through the range of pores that are occurring in the Vadose Zone. Shrink swell processes, fracturing, so mechanical processes will also be important. Here are some cracks that have formed in the Vadose Zone, and pretty clearly, if you're interested in the flow of water and air through the Vadose Zone, then the presence of these cracks will play a big role. So what we've seen is that there are several important controls on what's happening in the Vadose Zone, particularly for the development of soils. What is the parent material? So what's the composition of that? If you start with a quartz sand, then pretty clearly you would end up with a different soil than if you started with, say, carbonate that would be much more reactive, or something, parent material that had a lot of feldspar in it that could react to form clays. The climate will also be important, the amount of water that's available, the flow rate through the soil, the temperature, that will affect reaction rates, the extent to which wind is available to blow things around and do aeolian transport. Organisms, so the ecosystem that has developed on the landscape will be important, because that's going to cover who lives there and what they're doing to interact with the minerals and produce the soils. Also, the position on the landscape. If you have a landscape with even just fairly subtle highs and lows, these highs and lows are going to govern the movement of water, or affect the movement of water, and affect the saturation. And so when it rains, the water will fall and tend to migrate from the higher areas and accumulate in the lower areas. So even if this is just a very subtle change in topography, you'll find that the low-lying areas probably will have more water, higher saturation, and this will be less water, lower saturation. And so that will then control the chemical processes as well as perhaps some physical processes during the soil development. So you would expect soils to be responding to the landscape position, the slope, and perhaps even to microtopography. And then also the time that the soils have had to develop. The reactions that are producing soils, the chemical reactions, have fairly slow kinetics, and so the longer the time is that's available, the more the chemical reactions will proceed. So if there are leaching reactions that go on, relatively young soils, soils that say have been formed in an alluvial floodplain where the river deposits the alluvium really quite recently, these soils will be much younger and tend to be much lower amount of chemical leaching, say, than soils that were in uplands that have that are old uplands that have developed for quite a long time. Those soils will have chemical processing that certainly have the potential for being much more highly leached than say areas down in the lowlands that are receiving alluvial sediments.